Welcome back. So, we will continue with the mean field theory of the Ising model, and as I said repeatedly, in the mean field theory you have the dimension enters to the coordination number gamma, and which is by and large generally is a good approximation. There is no problem with that. So, the thing that we have already done is that the decomposition, which is this construction of this table, that this construction of this thing that we already said, the up spins is the plus, and whenever I draw a line from one up spins, only from the up spins to all the nearest neighbors. So, when I have two up spins next to each other, then there are two lines, and that becomes 2 n plus plus and those kind of things. For example, this is the condition that we derived, that gamma n plus equal to 2 n plus 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 n plus minus, and these are the kind of relations that we just did at length. So, these are the things again. So, this is the book from Carson Huang, and which is the best this from Carson Huang, and this is the best description of Ising model of the kind mean field theory Bragg-Williams approximation that I am talking here is done. This in this book of statistical mechanics. So, then one important thing in this process going through that. So, this was the kind of things that we have been discussing all this time, that the writing down the Hamiltonian in terms of this, what exactly I was telling before I do the mean field approximation. Then this is the partition function. This is fairly universal notation you find everywhere in the world. The same, every book will have this notation. So, that is a equivalence. That means this the field of Ising model and mean field theories are fairly well documented and well articulated, because this is a kind of so important that we have to be more or less in unison. Now, I just told you that this before I go to do the next step, there is to show the importance of Ising model, that this is applied to so many different things. One of them is the lattice gas. In the lattice gas, you say, okay, I have a lattice where I have if there is a gas molecule, then there is not, if there is, so I want in a gas where a lot of empty spaces, and I want to model that by saying, okay, if there is a particle, then there is a black, and there is no particle, that is empty. So, that simple thing essentially is again n plus. When there is a n plus goes over to your occupied, n minus is gas particles, but there is nothing there, and the two next to each other is n plus minus. If two occupied next to each other, n plus plus. So, you can now map the Ising model into lattice gas, and you can do wonderful stuff. So, then again, that as you said here, total number of lattice sites, then this total number of atoms that are occupied. So, in this lattice, when they are occupied, that is n plus plus. When they are empty, that is n minus, and total number of nearest neighbor pairs is n plus plus. So, exactly that thing. When you map that, you can now get the, and so if you say when they are next to each other, there is an attraction, and that attraction is epsilon, then that gives you that. So, it is like two parallel spins have a ferromagnetic interaction, and then I can write the partition function. I can write the partition function like that, and then I can now get the exactly decompose into this. Only difference is that the beta h term here is given by this term. But again I have to evaluate the same thing. G n plus n plus plus and e to the power beta h n plus n plus plus, that is this thing. So, I am done. So, one then number of ways of distributing atoms, n plus atoms into the n number of lattice sites. Now, something extremely important comes out of that. Then if my number of atoms, occupied atoms, my black dots or my here white dots, if that is equal to n plus, then I know n plus and minus n minus gives me the magnetization. And what does n plus gives me here? N plus gives me density. So, then I immediately have a wonderful isomorphism which is goes a long way, that magnetization is equivalent to density. That exactly correct turned out to be. That is the way we can transform one equation state of magnetic system into equation state for the gas liquid system. This is a far reaching consequence. So, now we now just discussed that how lattice gas model can be mapped into Ising model. We will next discuss one more interesting thing, and that is, these are all from Carson Huang. Now, the binary alloy lead brass, beta brass, and that is zinc and copper, and then I am now occupied, my lattice sites are occupied either by a zinc atom. I can now consider order disorder transition that takes place at 742 Kelvin in this case, that you can immediately see that my up spin could be copper, my down spins are zinc or other way around, and I can again write down a Hamiltonian. So, sure enough, I write down a Hamiltonian exactly same way. I now say, okay, my copper is energy interaction energy epsilon 1, epsilon 1, my copper and zinc, this is thing, and if I want copper zinc, then like that. So, this kind of binary mixture, we are talking binary alloy that they copper and copper like each other and zinc like each other, low temperature. Of course, here there is a more long range interactions because of the metallicity and all those things, but at a level high temperature, when you are talking order disorder transition, those things, but we have to say copper and copper like each other and zinc like each other, very much like a binary mixture that we do, and we will talk a little bit about that later. So, now I exactly have the same conservation rules. That means, I start with the 5, here these 3 numbers n11, n22 and n12, and then I have the conditions just I have done before, exactly same, that up spin, now copper and copper, down spin, zinc and copper and zinc n12, and copper plus zinc is total number of lattice sites n. And then I eliminate, and I now get my energy or Hamiltonian. I get energy Hamiltonian in terms of there n plus n plus minus, I get n1 and n1. That means n1 is number of lattice sites occupied by copper or zinc, whatever, and n11 when copper and nearest neighbors. So, these thing then exactly same what I have reduced to, exactly same that my Ising model. So, now I showed 2 cases, gas liquid transition and binary alloy, which are completely isomorphic to, and that in one shot explained beautiful many things. For example, if I do binary mixture, I give you just one example before I pass on, against density, then this is what gas liquid transition, and this is the critical temperature, Tc. Now, if I now do that with a mole fraction x of one species is exactly same graph. This is exactly same when I plot magnetization against temperature, because I already told you density is like magnetization. So, in one shot, in one formulation, you are getting three very vastly different phenomena, which is the magnetization, gas liquid transition, and order disorder transition and phase separation in binary alloys. This is just amazing. That is why one takes the Ising model so seriously, both in statics, equilibrium properties and testing, and our language of phase transition is completely dependent on Ising model. This is the most important system of statistical mechanics. Okay, let us continue. And this I was saying, this is the magnetic transition that is happening, magnetization against temperature. This is same as I can, instead of that, I can plot it rho versus T and exactly same thing. So, this is the classic critical point in magnetic system. So, order disorder transition, mole fraction, all these things are the same. This is one of the most huge success of the Ising model. So, now we go ahead and we complete our task of the mean field theory, and that will be now little bit a. So, the way we do now is this is order disorder transition that done in, I do not need to do that, but what instead I will do what I was continuing with. Okay. So, now the mean field theory is same, the way I am the level I am doing is Bragg-Williams approximation, and this is thing, and I need to make it little bit fatter. Now, so this I introduced long range order parameter and short range order parameter L sigma n plus 1, and these are the same thing, and now I make the approximation that short range order parameter is given by long range order parameter. So, the approximation is contained in the statement that there is no short range order apart from the long range order. That means, approximation states that statement that no short range order other than long range order, and once I do that, I do this, then I get n, when I make n plus plus by half gamma n equal to n plus squares, that translates into sigma, because this is nothing but remember the L plus n plus by n equal to half L plus 1 square, remember that, half L plus 1, sorry, and when I use that into here, I get this condition, that when I use this into in this into that, then I get this condition, sigma L plus 1. Now, that essentially means that I have the Hamiltonian now completely in Carson-Huang, H is my B. So, my Hamiltonian is then 1 over n, what is energy? 1 over H is half minus half gamma J L square minus BL. So, just make an note that his H is my B and his gamma my gamma, but his epsilon is my J. This notation I am using a little bit more modern, like we use J for Ising model, not epsilon, as Carson-Huang has used, and we do like to use Hamiltonian H but not E. As I use Hamiltonian for H, that deprives me of H for magnetic field. So, I use B, but B equal to H mu. So, there is no room for any confusion here. Once I do that, then I write down, now I am in a completely free domain. Now I know how to go. I know how many ways I can get n plus up spins in n, and that of course is n factorial by n plus factorial n minus n factorial. So, that is I have written here, and n plus is half n 1 plus L, the other is n 1 minus L. So, I can write n factorial by n plus factorial n minus factorial, then that is the way, or n factorial to n plus. So, that is the way I have written here. That is I have written here. This is the number of ways to distribute, and for a given configuration with L, because I started with n plus and n plus plus, that was the exact. Then I made the approximation, mean field approximation, and as a result of mean field approximation, I have only n plus. Then I go back, I already have L and sigma, and when I eliminate n plus plus, I eliminate sigma, I have only L, but in a consistent way, So, I have the Hamiltonian, and then I know how to. So, I put the Hamiltonian here, and lo and behold, I have fully. Now, I can evaluate that. So, in the large particle limit n going to infinity, I take the logarithm to get the free energy, and then I make the approximation. I make the Starling's approximation, just what we done in Mayer's theory, we have done in the canonical partition function. Again and again, we have picked up the maximum term. So, of the sum, I pick up the maximum term. Yeah, so, I remove that one, I take the log whatever remain, and then I maximize with respect to L, and maximizing with respect to L is same as maximizing with respect to n plus, right. So, remember, if you already have not noticed, note that L is nothing but essentially the magnetization of the system. And so, things are well and good. So, then we can go, and once we do that, then the thing that happens is that I get an equation which is the following, that okay, I get an equation by doing that, which is, let me write down because it is not very visible here, L equal to tan hyperbolic So, that is so this is called a implicit solution or a transcendental equation, where I have a L on the left hand side, I have L on the right hand side, and given a B, I have to solve that numerically. Now, if B is 0, the external magnetic field is 0, I have this beautiful solution, which is this one. That means L equal to tan hyperbolic in many places. Dimension k is introduced, which is j by kBt, then I L equal to tan hyperbolic k gamma L. Lo and behold, this has a beautiful phase transition scenario, that when we, so and this is given here, this phase transition scenario is described beautifully here, that when this has only solution of this equation is only solution is that is at when temperature is high. So, gamma j by kBt is less than 1, then even less than 1, only solution is L average, which is the maximum term. Actually, I prefer it L star, but that okay, L average, that only solution is the magnetization is 0. So, this is a random system. number of plus spins, up spins is same as number of down spins. However, a solution appears when you get a solution appears when you go to lower temperature. So, when you go to lower temperature, that means gamma j by kBT is greater than 1, temperature is small. So, this becomes greater than 1, then a solution appears, actually two solution appears, one of them up for up spins and that is for down spins, and you get the one can show that this root that 0 must be it corresponds to a minimum, not to a maximum. So, you can reject that term. So, then the solution reduces to the following things, that L these two solutions. To T greater than T c, you have no magnetization, disordered system. Below T c, it can be either plus or minus, it has to be 2, you cannot, in the absence of magnetic field, they are both are equally likely, there is no way to choose one of the other. The way the solution is made by doing a graphical method, which is shown here. The graphical solution is done in the following way, that you plot L and tan hyperbolic L, and then you, when they become equal to 1, then that is the solution, and the graph goes like this okay, it crosses here at 1 and crosses here at 1. So, these are the two solutions that you get, and it is a let me see if I can get it a little bit up. There should be something here, a cursor. Okay. So, this is the this line is the going selecting you when that become equal to tan hyperbolic and L. So, this is the L versus L, this line L line, this straight line, and this is the tan hyperbolic. You know the tan hyperbolic very well, because tan hyperbolics are like this, right, and these are the solutions when they meet, that is the solution of that, and that is L naught plus and minus solutions. Okay. So, this is part of these things, works out beautifully. So, next go to the next page. So, one beautiful thing of that is the following, of all these calculations is the following, that in general it can be obtained numerically, and one finds numerically some very interesting thing comes out, that near the critical temperature, when you are close to Tc, is a subject of great interest because of the what is called the critical phenomena, and we have done Landau theory of the critical phenomena somewhat. Then you find that numerically that this approximation, that L naught behaves is like that when you are away from the critical point, but when you are very in a region close to critical point, then the order parameter or magnetization behaves as Tc minus T to the power half. That means the magnetization varies sharply as a fractional exponent, and this exponent is called in a critical phenomena magnetic is called exponent beta. One is sorry to use the same beta in many different ways. This is the equation of state also. This is the same way rho varies as again Tc minus T, also the notation beta. In mean field theory, Landau theory, Bragg-Williams theory, all these cases this exponent beta is half, which experimentally found to be wrong. Experimentally one found, yes, there is a fractional exponent, and the basic thing is correct, that this is very singular behavior it shows. near the critical phenomena, but this exponent is more like 1/3. So, this is called equation of state exponent, and as I told you, magnetization same as density. In order disorder transition, again the probability of one being occupied by copper magnetization, or you can say composition, you know, of one minus other density of A minus density of the copper minus density of the zinc is exactly same thing. All now it need not be strictly 1/3, it varies from 0.36 to 0.31 and all these things, but essentially very similar. So, this is the essence of the critical phenomena and the critical exponents, and the critical exponents in many different forms, but this magnetization and density is specific. It also has a critical behavior that we will be discussing a little bit here. So, now here the thermodynamic functions are summarized for this. So, this is the magnetization, the L naught, and so this is the free energy, and then you get the, as I said, magnetization. This is the internal energy, and this is the specific heat that goes like that, and that behaves in the following fashion. It in this case it does not. So, specific in the Bragg-Williams approximation does not diverge, but it increases like that. So, this gamma j, I increase the this is my gamma j as I increase the temperature kBT, and it goes and saturates to a value like that, it increases like that. And then similarly one can go to lattice gas. This property comes from the this solution comes from this solution here, this thing, you can figure it out. So, that we just described in the previous page. Similar behavior you get in the lattice gas, very similar equations, that table of correspondence is given, and this is just exactly the same. One model maps into the other model, predictions are exactly the same. Same will be binary alloy. So, now this is what it is, this beautiful thing given here that I have been referring to all this time, that this is the gas liquid, all of you know van der Waals, that pressure versus volume, all you know this isotherm, and this is the critical point, and this is the inverse parabola that I was drawing as density versus temperature. If I plot against temperature, I get that the top is the critical point, and the lattice gas, equation of state in the lattice gas, and same in the, this is the mean field theory, simplest type of mean field theory, Bragg-Williams approximation, not too simple as we have seen, but it captures some aspects of the critical phenomena, but does not aspect the full aspect of critical phenomena, which requires far more work. And the same thing you get from van der Waals, the same thing you get from Landau theory, and you need to do lot more work to go beyond this level of approximation. So, next one level one does better with considerable more work is the Bethe approximation, but we are not going to do that. So, we'll stop here as far mean field theory goes. So, what did we achieve? We got a beautiful equation, L average or L we also got an equation, similar equation in the presence of the magnetic field, which is a little bit more complex, not too much. and both has to be solved numerically, but in some cases as you showed that one can do after doing the numerical work, there are some analytical work one can do and one get the magnetization as a function of temperature in a critical exponent beta equal to half, which is we call mean field exponent, and that does not do a good job. But what is the beauty of the whole thing is that it does describe the phase transition. It does capture many aspects of phase transition of three systems, which is magnetic, gas liquid, then binary alloy, order disorder transition in binary alloy. All the three, so it shows that these three systems to a certain level is isomorphic, and this was further in a beautiful paper that I recommend people to study by Young and Lee, in 1952 in Physical Review. He further pushed this analogy between Ising and lattice gas and binary alloy. Actually, some of these things follows what we have done follows from this classic paper Young and Lee. Then these two gentlemen got the Nobel Prize for their work on parity, but in 1952 they wrote two Physical Review papers one after another where they mapped the Mayer's theories. So, they connected the Ising model with Mayer's theory, and they showed that the cluster integrals that we do in Mayer theory can be expressed in terms of zeros of the grand canonical partition function, and huge number of results were done together, and all these beautiful fields of Ising model, binary alloy, all these things were put together in an epoch making paper of in these two papers, and what level mean field theory working, what level not working. So, that along with Mayer's theory and Ising model, Young Lee, those two papers played essentially the starting point or say launching point at sometimes often told to our study of the phase transitions and critical point. So, we might return later to the critical phenomena and a little bit more. We already have done the Landau theory, and we have done the concept of order parameter, and you see here already that in the free energy then ultimately described in terms of a L square term, and L is the magnetization, and Landau theory order parameter is the magnetization. So, Landau theory's expansion of free energy in terms of L square L4 is fully consistent with the Bragg-Williams or other way around, though Bragg-Williams has a microscopic basis. It starts with a Hamiltonian, but Landau just writes down the free energy expansion. So, it is quite satisfying to see that the Landau theory is recovered in a more consistent theoretical framework. And so, the concept of order parameter that we introduced in Landau theory, which is same as the long range order parameter L, which is same as the magnetization, which is same as the density, which is same as the mole fraction. So, Bragg-Williams approximation gives us a beautiful understanding of the free energy that is happening, the flattening of the free energy surface, all these things comes out of the Bragg-Williams. What is phenomenologically assumed largely on symmetry arguments and the basic physics by Landau. Okay, so we will stop here now. We will probably get to use Lee and Young again, and we will get to use Ising model again in the future course. Okay, we stop here now. Thank you.